Hey there, science fans! Today we're talking about helicopters, those amazing machines that can fly straight up, hover in midair, and even fly backwards. Have you ever seen a helicopter in action? They're pretty cool, right? But have you ever wondered how they actually work? It all comes down to the fascinating world of aerodynamics. Aerodynamics is the study of how air moves around objects, and it's the key to understanding how helicopters achieve flight. You see, just like airplanes, helicopters rely on the principles of aerodynamics to lift off the ground and soar through the air. But unlike airplanes, which use fixed wings to generate lift, helicopters employ rotating blades or rotors. Think of them as wings that spin. These spinning blades are the secret sauce that allows helicopters to perform their unique aerial maneuvers. Intrigued? Let's delve deeper into the fascinating world of helicopter aerodynamics. To truly understand how a helicopter manages to soar, hover, and maneuver through the sky, we first need to explore the four fundamental forces that govern its every move: lift, weight, thrust, and drag. These forces are constantly at play, working together and sometimes against each other, shaping the way a helicopter behaves in the air. Whether you're watching a helicopter take off, land, or perform complex aerial maneuvers, these forces are always present, acting as the invisible hands that control flight. Imagine these forces as four determined players in a never-ending game of tug-of-war, each pulling on the helicopter from a different direction. Just like in a real tug-of-war, the outcome depends on which side is stronger at any given moment. If one force overpowers the others, the helicopter will move in that direction. This constant balancing act is what makes helicopter flight both fascinating and complex. Let's start with lift. Lift is the upward force that allows the helicopter to rise off the ground. It's generated by the spinning rotor blades, which act like giant wings, slicing through the air and creating a difference in air pressure above and below the blades. This pressure difference produces an upward push, almost like an invisible hand gently lifting the helicopter skyward. Without enough lift, the helicopter simply can't leave the ground. Pilots control lift by adjusting the angle or pitch of the rotor blades, allowing them to climb higher or descend as needed. Opposing lift is weight, which is the force of gravity pulling the helicopter back down toward the earth. Weight is determined by the mass of the helicopter, including its fuel, passengers, and cargo. It's what keeps the helicopter grounded when the engines are off, and it's the reason pilots must carefully manage how much they carry. If the helicopter's weight is greater than the lift produced, it won't be able to take off or stay in the air. So, every flight is a careful calculation, making sure lift can overcome weight. Next, let's talk about thrust. Thrust is the force that moves the helicopter forward, backward, or even sideways. In helicopters, thrust is created by tilting the rotor disc in the desired direction. This is different from airplanes, which use engines and propellers to generate thrust. By changing the angle of the rotor blades, pilots can direct the helicopter's movement, allowing for incredible agility and control. Thrust is what lets helicopters chase after moving objects, fly over obstacles, or zip across the landscape at impressive speeds. But as the helicopter moves, it encounters drag. Drag is the force that resists the helicopter's motion through the air, much like the wind pushing against your face when you ride a bike. It's caused by air friction and turbulence as the helicopter slices through the sky. The faster the helicopter goes, the more drag it experiences. Pilots must constantly balance thrust and drag to maintain speed and control, making sure the helicopter doesn't slow down too much or use up too much power fighting against the air. These four forces, lift, weight, thrust, and drag, are always acting on a helicopter, no matter what it's doing, whether it's hovering motionless in the air, climbing to a higher altitude, or racing forward on a rescue mission. The pilot is constantly adjusting the controls to keep these forces in balance. Mastering this balance is what makes flying a helicopter both challenging and rewarding. For a helicopter to fly successfully, lift must be greater than weight, and thrust must be greater than drag. If these conditions aren't met, the helicopter won't be able to climb, move forward, or even stay in the air. Understanding these forces is the first step to unlocking the secrets of helicopter flight, and it's what allows pilots to perform the amazing feats we see in the sky every day. So, how do helicopters generate the lift they need to overcome weight and take to the skies? It's a question that has fascinated engineers, pilots, and inventors for over a century. Unlike airplanes, which rely on long runways and fixed wings, Helicopters have a unique ability. They can rise straight up, hover in place, and even fly backward or sideways. But what's the secret behind this incredible versatility? The answer lies in the ingenious design and operation of their rotor blades. The answer lies in the shape and motion of their rotor blades. These blades aren't just spinning sticks, they're carefully engineered to interact with the air in a very specific way. When you watch a helicopter, those massive blades slicing through the sky might look simple, but they're actually performing a complex aerodynamic dance. Remember those spinning wings we talked about? Those are the rotors, and they're the key to a helicopter's lift-generating abilities. Each rotor blade acts like a wing, but instead of moving forward through the air like an airplane, the blades spin rapidly around a central hub. This spinning motion is what allows helicopters to create lift without needing to move forward. Helicopter rotor blades have a special curved shape called an airfoil. This shape is crucial because it manipulates the flow of air above and below the blade, setting up the conditions needed for lift. If you look closely at a rotor blade, you'll notice it's thicker at the front and tapers toward the back, with a gentle curve on top. This airfoil shape is similar to the wings of an airplane, and it's what helps to create lift. Both airplane wings and helicopter blades use this design to take advantage of the principles of aerodynamics. The difference is, while airplane wings move the whole aircraft forward to generate airflow, helicopter blades spin in place to achieve the same effect. When the rotor blades spin, they force air to flow over their curved surfaces. This movement of air is essential because it sets up the pressure differences that make flight possible. The faster the blades spin, the more air they move, and the more lift they can generate. This creates a difference in air pressure, with lower pressure on top of the blades and higher pressure underneath. This pressure difference is what pushes the helicopter upward, counteracting the force of gravity. It's the same basic principle that allows birds to fly and airplanes to soar, but helicopters achieve it in a way that lets them hover and maneuver in tight spaces. Imagine placing your hand outside a moving car window. You can feel the force of the air rushing past your hand, and if you change the angle of your hand, you can feel it lift or push down. If you tilt your hand slightly upwards, you can feel the air pushing your hand up. This is a simple demonstration of lift, and it's exactly what's happening on a much larger scale with helicopter blades. By adjusting the angle or pitch of the blades, pilots can control how much lift is produced. In fact, helicopter pilots have special controls in the cockpit that let them change the pitch of the rotor blades while they're spinning. This is called the collective, and it allows the pilot to make the helicopter rise, descend, or hover with incredible precision. It's a level of control that fixed-wing aircraft simply can't match. That's the same principle at work with helicopter rotor blades. By carefully controlling the angle and speed of the blades, helicopters can generate just the right amount of lift to take off, hover, or land gently. The faster the rotor blades spin, the greater the difference in air pressure, and the more lift is generated. But spinning those heavy blades at high speed takes a lot of power, especially when lifting the entire weight of the helicopter and its passengers. This is why helicopters need powerful engines to spin their rotor blades fast enough to produce enough lift for takeoff. The engine's job is to provide the energy needed to keep the rotors spinning, even when the helicopter is carrying heavy loads or flying at high altitudes. Without this power, the helicopter simply couldn't beat gravity and rise into the air. So the next time you see a helicopter hovering effortlessly above the ground, remember the incredible science and engineering at work in those spinning blades. Now, to really understand how that pressure difference is created, we need to talk about a couple of important scientific principles: Bernoulli's principle and the Venturi effect. These two ideas are at the very heart of how helicopters, airplanes, and even some of the things you see in your kitchen every day actually work. They might sound a bit intimidating at first, but once you see them in action, you'll realize they're not just clever theories. They're the invisible forces that make flight possible. Don't worry, they're not as complicated as they sound. In fact, you can see these principles at work all around you, from the way a shower curtain gets sucked inward when you turn on the water, to how a perfume atomizer sprays a fine mist. But in aviation, these principles are absolutely essential. Let's start with Bernoulli's principle. This fundamental law of physics states that as the speed of a fluid, like air, increases, its pressure decreases. Imagine air as a crowd of people. When they're moving slowly, they can push against you with more force. But when they're rushing past quickly, there's less time for them to push, so the pressure drops. This is the key to understanding how wings and rotor blades generate lift. Now picture a helicopter rotor blade as it spins through the air. The blade is shaped so that the top surface is curved, while the bottom is relatively flat. This design means that the air traveling over the top of the blade has to cover a longer distance in the same amount of time as the air moving underneath. To keep up, the air on top speeds up, while the air below moves more slowly. Because the air on top is moving faster, Bernoulli's principle tells us that its pressure drops. Meanwhile, the slower-moving air underneath the blade maintains a higher pressure. This difference in pressure between the upper and lower surfaces of the blade is what creates lift, the upward force that allows helicopters to rise off the ground and hover in mid-air. To help visualize this, think of a river. When the river narrows between rocks, the water speeds up and the pressure drops. In the wider sections, the water slows down and the pressure increases. This is a perfect analogy for what happens to air as it moves over and under a rotor blade. The water flows much faster in the narrow sections, just like air speeds up over the curved top of the rotor blade. In the wider, calmer sections, the water slows down, similar to the air moving beneath the blade. This simple river analogy helps us see how changes in speed and pressure are connected. The same principle applies to helicopters. As the rotor spins, it slices through the air, creating regions of fast and slow airflow, and therefore regions of low and high pressure. This is the secret behind a helicopter's ability to lift off, hover, and maneuver with such precision. Now let's talk about the Venturi effect, which is closely related to Bernoulli's principle. The Venturi effect describes what happens when a fluid, like air or water, flows through a constricted or narrow section of a tube or channel. As the fluid enters the narrow part, it speeds up, and its pressure drops, just like the river rushing between rocks. You can see the Venturi effect in action in a laboratory using a Venturi tube, a specially shaped tube that gets narrower in the middle. As air or water flows through the tube, it accelerates in the narrow section, and the pressure drops. This effect is used in everything from carburetors and engines to medical devices that deliver oxygen. In helicopters, the shape of the rotor blade acts like a built-in Venturi tube. The curved upper surface and the angle at which the blade meets the air create a constriction, forcing the air to speed up as it flows over the top. This acceleration further reduces the pressure above the blade, enhancing the lift generated by the pressure difference. So, both Bernoulli's principle and the Venturi effect are working together every time a helicopter takes to the sky. The faster moving air over the curved blade, the lower pressure above, and the higher pressure below all combine to create the lift that keeps the helicopter airborne. The design of the rotor blade is crucial. Engineers carefully shape and angle the blades to maximize the speed difference between the air above and below, ensuring the greatest possible lift. Even small changes in the blade's shape or angle can have a big impact on how much lift is produced. Thanks to the brilliant insights of Daniel Bernoulli and the practical applications of the Venturi effect, we can understand why there's lower pressure above the rotor blade and higher pressure below it. This pressure difference is the magic ingredient that allows helicopters to defy gravity. So the next time you see a helicopter hovering effortlessly in the sky, remember, it's not just the power of the engine or the skill of the pilot. It's also the invisible dance of air pressure and speed, choreographed by the principles of Bernoulli and Venturi, that creates the lift force pushing the helicopter upwards and keeping it aloft.